cluster of computers, how hard is it to for me to set up a Julia cluster or run Julia code on these clusters?
So it depends on how you want to do it, but I've actually never. Viril, how hard is it to do that?
It's actually very straightforward, and I'll just show you right now.
You're going to do it?
Well, I don't have a cluster, but I'll
So distributed memory cluster to.
You'll get an idea.
Okay.
So Julia, so I have J. Can you see what I'm typing here? Like
Yes.
Yeah. So I have J alias to my Julia setup, and I can just say J-P. It's my laptop, so I can say 4, and it's going to use. It's going to spawn processes locally and start up Julia with 4 processors right here. But we have this other big machine over at MIT. I don't have a network here, sorry.
Oh, you could if you want to. If you go to PayPal Guest and what was it? Safe payment? With capital S, capital P.
Free payments.
Is that it?
I think so.
Capital S, capital P.
What?
Yeah.
Okay, but well,
Payments with an S.
Payments.
Oh, okay.
So you can say nprocs out here, and you got the one that you started with and 4 more. But if you want to do real cluster, then you just type Julia's help, and there is an option here to provide a file name, a machine file name, which basically will SSH into each one of those things and start up the whole thing.
So all you need are IP addresses on
Yeah.
a bunch of. There you go.
It actually the story gets better than that. So what we have is a cluster manager interface, and what that says is that given any kind of cluster that you have, Julia can kind of figure out how to run the right commands to allocate resources and start it up. So for example, people have written a cluster manager. So cluster manager is a common interface, and people have implemented it for SunGrid engine. They've implemented it for MPI programs. They've implemented it for Amazon EC2, so you could allocate a cluster there, and it's completely extensible. So if there isn't one for what you need, you can write one within like probably 20 minutes or something. Basically, the concept of how to log in, how to get a machine, how to log into it, how to start a Julia process. That's all it needs. Let me see which ones. But the simplest one is SSH. So if you can SSH into all the machines you care about, then you've just provided a list of IP addresses and you're good to go. All right. So I think that answers that question.
Are you still setting up? Should I take another question?
Yeah, we can keep taking questions. I'm ready to go as well.
It's certainly true that like anytime when one gets these questions, like is it easy to do a cluster? Every time people keep coming back to me and saying, it is easy. And the reason why these things are easy is again the flexibility of Julia's language, the fact that you can simply swap one thing to another, and so you can very productively make these things easy for the users. So it just that's what I keep hearing, that these things just work. Any other questions?
Okay. I'm just going to try and go into that machine if SSH is allowed on this network.
It should. Is the machine up?
The machine's up, yeah. There it is.
Okay.
This is a pretty big machine, so if you do, it's got 160 cores on the same machine. And then if you do top, you can see that, well, it can't even print it, but it's got a terabyte of RAM. So it's unfair, right? Yeah. But you can. I think this thing is not liking the fonts. Is this readable at all? It's kind of small, right? It's fine at the back. Okay. So I don't have my alias here, so I'm just gonna go. Let's see. This is the development branch of Julia, so I don't know what's gonna break as I do things. But just to give you a, let's just get 80. So it's actually hyper-threaded, so it's really just 80 cores. And maybe just to be nice to some people who might be using the machine, let's just get 70 of them. And so Julia is launching 70 of these things as I kind of sit back and look at it. But there we go. So I can do nprox. So one of the things that that you do in Julia is peak flops. If you know,
that
that's
says 71 because there's sort of the
one I'm typing into, and
right, and then the 70 that you've added.
So this is peak flops, and this is peak flops for. Let's just run it again just to be on the safe side. So peak flops is a simple function that basically picks a couple of matrices and multiplies them and then computes the maximum floating point rate that your system gives you, and that's what it does. But if I really wanted to know peak flops for the entire machine, I would have said I would write a Julia comprehension and go for I equals 1 to nprox, and I get. What's going to happen is that for every processor, it's going to run peak flops, and then it's going to return a value and stick it into a vector. And so it's setting up. Now, one of the things that happens, you see that it's taking a bit of time because these are separate Julia processes. I'm not doing multi-threading, which is what Alan talked about in the last slide. So multi-threading in Julia is a little new, and it's stabilizing. It's going to be there in Julia 0.5, which is a few months away. But in the meanwhile, we need to do multi-processing, which means every Julia processor is getting this peak flops function, and it's JIT compiling it, and it's going to take a while it goes through it the first time.
Did you need an parallel or something?
Nope.
How does it know what processor to run on?
I'm just counting the flops of every machine.
How does it know that it's every machine?
Did I? Oh yeah, thank you.
I think you're just running it on the.
I'm just running it on.
Zero.
Yes. Okay. Thank you for pointing that out. So I would have to do at parallel for I equals nprox peak flops, and then I would have to do that. All right. So this is your sort of simple version of.
You should have done a VCAT or something. A parallel VCAT.
You want me to do a VCAT and then plus maybe?
Rather than reducing it, yeah. Then we could actually look at the numbers. See if they're all equally strong or not.
Right. So, these are the numbers. So they're kind of all the same processors, which is kind of what you'd expect. This is your MapReduce parallelism, right there. It's a very simple thing, but what's happening in Julia is that you've got this for loop out here, and at parallel. So the at symbol specifies that something is a macro, which means it's going to take this for loop and transform it into something else and run it in parallel. And in this case, what it does is it'll assign each iteration of the loop to a single processor. And since I'm running the iterations from 1 to the number of processors, every processor gets one thing. And then the body of the loop is your map, and then this thing out here is your reduce function. So earlier I had done plus, and it just gave me one number, and I'm just going to run it again. So it's 71 times this number, and that's 527 gigaflops. So that's about.
That is multiple process.
Sorry?
Did you say that it's multiple process rather than threading?
Yes. This particular one is running multi-process.
I actually I would love for you to go left parent STD, right parent. I'd love to know the standard deviation. Just replace the plus with an STD.
So this is half a teraflop.
That should work, right?
Yes, it should work.
I'm very curious what the variance is among those. The actual subtle differences between the processes. When you have to go x goes to STD of x, maybe? That's the only thing I don't know. I think you have to write an anonymous function. I shouldn't do this to you, bro.
I'm happy to take more requests.
All right. Don't you have to go x slash greater than? Yeah.
I don't think that's going to do it, but let's try it anyways.
If that doesn't work, then I'll just show it.
What do the error messages say essentially?
Here, the error message is saying that, I mean,
Oh, never mind.
so the error message is basically saying that it's looking for a reducer and it doesn't find a reducer that works with standard deviation. But I could have probably done mean and it might have worked. But anyways, enough of sort of trying stuff on the fly. I hadn't planned to do any of this. Since the question came up, we just started. But I think the basic point here is that you can start up Julia in parallel, and you can run Julia code on each processor and kind of do what you want to do. And that's pretty straightforward. But you can build on top of that many more complex parallel structures. So how would you use this to write the alternating least squares algorithm? I think there had been a talk from someone here. I don't know who, but is the person here who gave the ALS talk?
Yeah.
It was you. Okay. I have some of your slides that are stolen, so they're coming up soon. All right. So as I go through some of my slides and some of these things, I will, I'll go through things. I think there was a quick question about multiple dispatch. Should I just write a little bit of code, or do you guys want to go through the slides and look at some GPU stuff, parallel stuff? Is there code? Okay. Let me see if I can get a bigger console. All right, let's just use this one here. So this is your typical, this is your Julia REPL. You just start out and, I already did the peak flop, so what would I do? One of my favorite things in Julia when I start out to show things is just rand, and you get your random values, and then you do, 10 to the 6, and that's your million random values, and then, that's, if you realize that the first time there was a little pause, let me just, now that I've mentioned it, let me just show it to you again. So this is my first, and there's a little pause. This pause keeps getting smaller to the point that I can't show it anymore. And that's the JIT pause, basically. It's the first time you run something, Julia is JIT compiling that function, and then it's storing the assembly generated and it's running it over and over again. But we just keep adding more and more tricks. Our compiler guys keep adding more and more tricks, so you can't realize the JIT slowdown anymore. It used to be more pronounced before. Okay, so...
Sorry, can you move the terminal to your left?
Sorry?
Can you move the terminal
Oh, yes, okay.
to your left?
All right, and let's just maybe turn this out of the way. And let's get that there. Okay. So I have my, so the usual matrix algebra works. So I can do A plus A, or 2 times A, or, square root of A, and all that stuff just works. I can do the norm of A. I can create matrices. So normally distributed, let me just do a 5 by 5. So you can see the pluses and the minuses there.
Can I ask a question?
Yes, please.
You compile things again and again back then, right? So wouldn't that do things to your rank? Then what if for people like us, we don't have 1 terabyte rank? So does it do garbage collection automatically at the back or something?
Yes, so the language is garbage collected, and it will figure out when things go out of scope, and it will eventually run a garbage collector and clear it out.
So it does all this automatically?
Yes, in fact, we actually expose what happens in the garbage collector. So I'm going to time something soon, and you'll see how the garbage collection kicks in. Right, but it does it automatically. It's a generational garbage collector in Julia now. So every time the garbage collector gets upgraded, everyone's codes just suddenly magically start working fast, as happens with all garbage collected languages. Okay, so that's your, and the fun one, you can always do your 1000 by thousands, and then we don't print the whole thing. If you're a MATLAB user, you'd be frantically hitting Control C right now. But we've got these nice Unicode dots out here, the vertical one. Okay, so you could do your matrix multiplication, and that works just fine, and you could do your matrix divisions, and those work fine as well. So that's pretty fast, and I can time this operation. So, and I'm not going to print the result, I'm going to just suppress it with a semicolon. So I'm trying to push the garbage collector. There you go. So this time a garbage collection run happened, which means this was a little slower than the earlier ones, and it said 12% time spent in GC. So So as you run more and more complex programs, you'll start seeing the effect of garbage collection. Okay, that's enough about matrices for now. What I really like to show is things that you can't easily do in similar languages that I think you can't. And one of the things that I personally, when I programmed Python or R, well, I haven't programmed R much, but I've done a lot of Python and MATLAB. And in many of these languages, if you use the built-in types of the system, everything is great. Well, in MATLAB, everything is double precision. Well, I guess technically it's a double precision complex or something. But now MATLAB has many other types, but Python kind of, if you're doing numerical linear algebra, you're pretty much stuck with the basic types. Julia actually exposes much more to you. So not only what Julia provides is fast, but what you write in Julia is equally fast. And the reason is that there is no distinction between the person who wrote the Julia base library and you, the user. Everyone is essentially getting access to the same compiler, the same stuff under the hood.
Can I just sort of reinforce that just a second?
Why not?
When I started using Julia, it blew me away that I could go in and tweak these lower level things. I was used to some of these other languages, like Viral was mentioning, and I always sort of figured that oh, I'm not allowed to go and change that. That's for some people over there to do. I don't have the right to go and change those things. But then when you start to go in there and realize that you can just fiddle with anything, and it's not dangerous. Well, maybe it is dangerous, but it's powerful. I mean, you really have that power. It turns you into a Superman, right? I mean, you really you start to realize that you don't have to wait for somebody else to provide you with something in 3 years. You can have it today.
So here's you would have thought that something like 1 + 1 would be so buried deep inside your compiler and language that you wouldn't even be able to find where that happens. Typically it is, even in some of the simplest programming languages and cleanest ones like Scheme, it's pretty hard to find where all this stuff gets done. In Julia, you can just put @which in front of any method and it will tell you what method is running. So I said @which 1 + 1 and it said it's at int.jl line number 32. And this is int.jl, so this is the Julia source tree, and then I go to base, and this is the entire Julia standard library. Which is much larger in size than the actual C code that is, running inside Julia, the runtime. And then this is line 32 right here.
Actually, if you were in the Jupyter Notebook, you could have just clicked on the hyperlink and it would have
Yes.
gone right there.
Yes.
You did it real fast, but it would have been even faster.
Yes, if you're in the Jupyter Notebook, you would get this as a hyperlink actually. And then you can just click it and it'll take you to the GitHub page for that thing. But I like to use Emacs and the terminal. It's more fun for demos. So, and so what's happening here? So addInt is an llvm intrinsic, and then it's unboxing the two inputs, and then it's boxing them back, and then the compiler, when it runs, it's going to figure out based on the types whether the boxing is essential or not, and it can get rid of it. So all the usual stuff. But this is kind of how a lot of the code looks. I mean, and so user-defined types. I'm still not using a user-defined type, so I'm going to get there in a couple of minutes. But so here's a common example, right? A factorial of 20. What do you think is going to happen? Is it big enough to do something, or? So if you have 64-bit integers, that's fine. So I'm on a 64-bit machine, which means my default int is 64-bit. But it's going to die at factorial 21. But I can go .o, and now I'm in double precision. So I'm now doing factorial in double precision. As a result, I got the answer. But I really don't like, losing all those digits at the end. So I'm just going to say big of 21. And that worked because now I have a big integer. So type of big of 21. And that's what you got. And now I can just, go like that. And it just kind of keeps going. I don't know if I'm going to not like this.
It'll be about 10 times the real estate. 10 times real estate.
Yes. But you can kind of get, you can get integers as big enough to fill up the memory of your machine and then crash. Like it's possible. So people who do research with with all the cryptography stuff and like factorizing large numbers, like they usually like all these kinds of things. And also this doesn't have to be restricted to just the big goes to floating point as well. So you can have arbitrary precision floating point should you want to.
128 bits for the integer?
Sorry?
Is that 128 bits?
For the integer, yes, you can get a 128-bit int. That's a native type.
But the big is 128.
The big is actually arbitrarily big. It can be as big as you need for the number to be stored. So
It's a VPA system.
So this is the largest number you can store in 128. But big can be even bigger than this. It can take as many bits as you need. All right. So this is fine. I mean, these are all the built-in types. You can see it kind of all works very well. It works very fast. What if I wanted to write a new type? And this is where a lot of the other, this is where the Julia's JIT compiler and its language design really sort of start shining. Is, if I want to write my user-defined type, and I'm just going to go with my usual example here, which Alan is not a big fan of, but I'm going to go for it.
I'm growing to like it more.
Okay. All right, I'm just going to type it right here. I'm not going to recollect it from memory. So I'm just going to create a point. I'm going to parameterize with t. So this is, and it's just going to have x, which is of type t, and a y, which is of type t. So if this is pretty straightforward. It looks like a C struct, right? It's got two elements, got two fields, x and y. You can imagine it's a two-dimensional point with two x and y coordinates. And the t out there with the curly braces is actually is what we call a parametric type, which means that when you create a point based on the inputs you're giving to it, Julia is going to figure out the type and substitute it in that t. So parametric type. So it's easier to see it when I do it. So if I do this, I get a point which is two integers. But if I do this, it's not going to work because you need both the types to be the same. But if I do this, then it works. I could have had t1 and t2, and then x was t1, y is t2. Julia also has promotion rules and conversion rules, so I can automate all of this, which is what happens under the hood when you do mixed precision arithmetic. But I'm not going to go into that direction at the moment. So we've got a point now, and we know how to create. We know how to create these points. Okay. So what if I wanted to add 2 points? And the usual definition is I would have to import. Before I can do that, I have to import the plus operator from base and bring it into my workspace right now. And then I will say, let me just see if I can avoid typing this. Yes. So if I want to add 2 points, a comma b, then I'm just saying they're the sum of their x's and the y's. So I did that. Oh, by the way, so when I did this, it says plus. The generic function plus has 165 methods. So you might be wondering what are the other 164. And you can ask Julia and it'll tell you. So you kind of start from right up at the top here and you say, this is just a unary plus on a Boolean value. And then you kind of start scrolling down and at gmp.jl line 256, Julia is telling you how to add 2 begins. And then you kind of go forward and yeah, that's how you add, big floats. And then as you go forward, this is code that's working with ranges. How do you add 2 ranges? How do you add arrays? How do you add different types of arrays? What Alan was referring to with the linear algebra stuff. How do you add a upper triangular array to some other array, for example? How do you add diagonals? And it goes on. And then how do you add dates, right? I mean, you could take a date and add days to it, right? And it doesn't stop there. So you can extend plus to mean something else for your own types, and that's what I just did. So now if I have, let's just say I have a equals point of 1, 2 and b equals point of 1, 3. Let's say 3, 4. So a plus b, it just worked right away. No compilation, nothing. Okay. What if I wanted, and I can bring in base.star at the same time, and I'm going to go with the simpler one first. What the hell? We're going to do this one. This is going to be more fun. Okay. So I'm just defining matrix, I'm defining the multiplication of 2 points to be just this formula out here.
See if anybody in the audience recognizes what.
Does someone know what? Yeah, you probably know it. Yes. So this is complex multiplication. If x was the real part and y was the imaginary part, that's what you'd get. So I'm gonna just write that, and Julia also has another 139 methods for star when you start up. Okay. So if I have plus and star, okay, but let's do a few other things. So now that I have this syntax, I can combine it with comprehensions, and I can say, let's say point of I comma j, well, let's say point of I for now, for I equals 1:10, and I think I wanted to say I comma I, but it doesn't really matter. So here, I'm going over the values. This is a single, this is a comprehension that's just generating a vector. I could have done, you can do, let's say equals 1 to 5. So I can just do that, or, you can just do that, or you can just do nothing inside and just get the shape. So here's a way to get random points in a plane, just like that. All right. So let's just get this and call it the matrix A. So I have a random matrix of points, and so the point here is, pun intended, but the point here is not to work. Is not to sort of belabor the point about generic programming, which I think you guys are probably already following, but to show that things that you haven't defined but have been defined under the hood just work automatically. So do you think if I went like that, should that just work? I mean, if I have a type and I've defined a plus and a star on it, should matrix multiply just work? I mean, I would think so for the most part. And it doesn't, because it still needs you to tell, inside of matrix multiply, it's going to call a reduction somewhere, and it still needs to know what the additive identity is. So I'm going to bring in one more function. So how do you initialize the 0 value when you're going to have your for loop? You got to initialize something to 0 before you add stuff to it, right? And then I'm going to say 0 of a point is just that. But I'm working with ints out here, so let's just make these ints. And well, there were 14 zeros also before we started. Okay, I think I now have everything to make this work. Oops.
I have a question.
Sorry, yes.
In this import currently thinking, so there are already 15 methods defined on 0. Are they all in base? Why they are imported?
Yes.
Okay.
Yes, they are all in base. Absolutely. All right. So what?
You have to define a 1?
I don't need a 1. It turns out it's still not finding a 0.
Yeah.
So.
The floats and ints. Oh. Yeah, you define the int 0.
Okay, maybe I should do it for floats as well. Because I'm doing a times b, which is a float. Sorry, I moved away from my integers. All right, let's just do it now. So a star b just worked. So Julia has a generic matrix multiplication, which will. So you can almost imagine what is happening under the hood. When you give it to matrices, you all remember your formulas for matrix multiply, and it's doing the plus and the star and all this stuff under the hood. And Julia is going in and saying that, the input is a matrix of points, and hence I need to call plus on points, and then it looks at the plus method table, and it's like, I found that, I found the star, I found the 0. It's putting it all together. And this is running at native machine speed. It's almost like if you had written this in C, you probably would have been roughly at the same performance level, maybe a little bit here and there, but by and large, this is going to be code that Julia is able to type in first. So this is, as you go deeper into like what Alan was saying, like the whole talk for explaining why Julia is fast, one of the reasons is, this is multiple dispatch at work, right? How do you add 2 integers versus 2 floating point values? So the reason Julia's fast out here is because it's got all this code, it's able to do type inference of the matrix multiplication. It's going to figure out that it's all points inside these matrices, and then inside the points it's all int 64s, and then it looks inside the addition for the points and it says, it's just doing integer addition out here or floating point addition, and it infers all this stuff and then just generates like machine code that does exactly all of that. And you can.
This is quite opposed to some other languages which at runtime it spends all its time figuring out, which of the various pluses it's doing, while you're sitting and waiting for it to make up its mind. And so Julia as a language in a way is helping the compiler. And so that's why sometimes people ask, could we take whatever the magic is that makes Julia fast and put it into some other language? And I think, you could, by and large, the answer is probably not so much.
So here's a simple, and here's a simpler version to show you what's going on under the hood. But I just wrote a simple function. So you can write functions with one-liners like that. So f of something equals, it's kind of handy. And then you could just, just do add code native, and you can see the assembly under the hood. And that's kind of fun sometimes. And you see that if I give it an integer versus giving it a floating point value, it's doing something different. You've got all these V's out here, which suggests that there's some SIMD stuff, SSE stuff going on there, and that's more integer kind of stuff going on up there. I think we could even have seen what's happening in the other case where we did the matrix multiply, but that's probably too much.
Sorry, is this actual assembly or is it like bytecode for a virtual machine?
No, the bytecode is like this. It's a good question. So if you can see the llvm bytecode, that's what the bytecode looks like. And well, if you really wanted, so let me just show you the whole thing. This is the lowered version of the expression that I typed in, which goes to llvm like that, and then that goes to native code. So that is the actual native code. Yeah. And I guess this is really the reason why Julia is fast, because it took this complex high-level definition of matrix of points and it was able to boil it down to small, tight assembly. And this was the why the sorting algorithms run fast, right? It's boiling it down to fewer data movements. Okay. So maybe I'm just going to switch to a few other developments that are happening that you guys might be interested in, and I can switch back and forth as necessary. So these are some of the things that we've been doing. So we've taken this basic language base, and on top of this we're building a new parallel programming model. We are experimenting with it, so we don't know what the right parallel programming model for Julia is. But there are all these models that people have experimented with over the years, and it turns out it's very easy to implement them all in Julia and get a feel for it, and that's what I'm going to do. So first, I'm going to start with GPUs. So Julia and GPUs? I think a lot of people out here are who's using GPUs already? There's like 5-6 people. All right. So you've all heard, right? Like this GPU thing out there, this NVIDIA thing is like a teraflop in a $200 card, and the big Intel machine that I just ran on was like half a teraflop with 80 cores. And that probably would have been, I don't know, $50,000 or something like that. And for $200, you can have this thing so cheap. So Arrayfire is a fantastic open source library that Julia uses. That's a C++ library that has a common backend for OpenCL, for GPUs, and for CPUs. And one of the first things we did when we started working with GPUs is that we'd like to use all the functions in Arrayfire under the hood in Julia, so that when you create an array, you would just get an array of, you'd get an Arrayfire array that's on a GPU, so that when I overload the plus method, instead of doing a plus on a CPU, it's going to go ahead and do the plus on the GPU. I don't know if this code is readable. I think it should be okay. So this is Julia code working completely on GPUs, because it's actually offloading all the computation to the GPUs using Arrayfire. And so here's your rand, your random, and you kind of have to look really hard at this code to tell that this is not the standard Julia code that I was running just a couple of minutes ago, but this is GPU Julia code. And the reason is it's got this F. It's instead of array, it's AF array. So you just have to sort of stick AF in front of the array, and you get an Arrayfire array. And then because of the magic of multiple dispatch, everything just goes through. So you've overloaded sign, star, plus, determinants, absolute values, dot star, transpose, LU factorizations, pure factorizations. So if you had a GPU on your machine and you installed Arrayfire, this would all just work. And so this is already beginning to get interesting, right? Because it's pretty hard to program for GPUs, but if you write vectorized code, which probably many of you do if you're using either Python or MATLAB, you could write vectorized code in Julia and leverage GPUs right away.
Sorry, question. Is it safe to say that you can just put A times B into a post-to device?
Into a?
Post-to device. You just put A times B instead of random.
Instead of random, I don't understand, sorry.
Because for this code, you're just telling the GPU to generate random numbers.
Yes.
So can I replace ran 100 with A times B?
Well, you still need your data, right, to start off.
I mean, yeah, correct. So how do I transform operations?
Right here, it's if you say AF array of data that's on the CPU, it's going to go to the GPU, so it's host to device, and then device to host is array of that. So it's a type constructor. So if I say AF array of a matrix that's in my CPU memory to take it and put it on the GPU, and if I say array of something that's on the GPU, it's going to move it back to my CPU memory. And so then you can do this, and then everything is. So yeah, I think the question, maybe what you're referring to is you have to explicitly do these kinds of things. Julia cannot yet sort of do these automatically for you. And one of our hopes is that as we sort of push towards more and more, you push deeper into parallel programming models, we can infer enough of these kinds of things and auto-insert some of this data movement in there.
You've got multiple cards.
No answer at the moment. You mean multiple cards on the same machine? Because if there are multiple cards on different machines that just run different Julia processes. I think
at parallel would be fine, right?
Then at parallel would be fine. So I think the question you ask has a couple of answers which go beyond just plugging ArrayFire into Julia. So ArrayFire is going to have multiple GPU support soon, and you're going to be able to use it transparently anyways. So I don't think that's a big deal. But what you really want is not just ArrayFire, but you want to write arbitrary Julia code and execute it on the GPUs, right? And that work has actually started off. There are a couple of guys who are working on it for their thesis, and we expect in the summer there's going to be a lot of progress on code generation from Julia to GPUs going forward. And the GPUs are kind of also getting nicer over the years, so they're more programmable. And so today we do code gen for x86, we do code gen for ARM. ARM is almost complete. We're working on Power now. Slowly, Power will come along. Power already starts up. So if you have a Power machine, IBM Power, you can actually start up Julia and do most of the things. It's like 70% passes the test suite. ARM passes like 95%, I would say. Total gut feeling at the moment. I haven't actually counted this time. GPUs are like probably 0% at the moment, but as the code gen comes in, we'll start seeing how that goes. So one of the things is that we really are committed to making Julia work on all varieties of hardware that comes along, and being on llvm makes it a lot easier to do it. I mean, I'm sure like many of you who've seen like or worked on older compilers, you could never even imagine just like saying like, oh, I'm just going to take this compiler and port it to this other random architecture. It's just the world has become so much easier nowadays that you can actually do these things. And I think for this reason you're seeing newer kinds of hardware come out. There's a Xeon 5 from Intel, there's the Knights Landing that's coming out. There's no shortage of these GPUs, there's the AMD and the NVIDIA versions, and there's people going down, with smaller and smaller ARM machines. So our goal is that we never want people who write in Julia to rewrite their codes just because they're going to run on a different architecture. So we being the community likes to be able to run the same Julia code on everything. So we have people writing Julia on Raspberry Pis, we have people putting Julia on quadcopters, we saw the 3D printers, we have people putting Julia on supercomputers. It's kind of fun seeing all this stuff work. Alright, so very quickly, I just thought I'd show this just for fun, but this is the wrapper. This is how the ArrayFire is plugged into Julia. If I showed you how to write an interface to a C function from Julia, that would be impressive, but like you could probably do it in anything. Let me just show that to you really quickly anyways. So if I wanted to call a C function, I just say call, and then I type the name of the function, its return value. Sorry?
Let's see what we get.
Oh, this is one of those things. I need to go out of the PowerPoint, I think. Alright, so call means call a C function, and So you don't need to have a C compiler installed. It's going to push, it's going to push the arguments onto the stack and then reset your instruction pointer and then go ahead and do all the stuff. That's good. I mean, for C is a much simpler language, but what happens when you're in C++? And turns out that things are not as straightforward. So we actually have an extension that Ken Fisher, one of our, one of the founders of Julia Computing and one of our colleagues wrote this thing called cxx.jl. cxx.jl right here. And the way it works is you say icxx and then you take a string and you put in a C++ expression inside and the dollar, that string interpolation going on in there. So that A is going to be passed in there. So you pretty much get the full C++ specification. You could do templated C++ code in Julia on the command line. You can actually do interactive C++ in Julia today because of cxx.jl. I was trying to compile cxx.jl on my way here, but it needs to rebuild the whole world, from llvm and Clang and all that stuff. But the whole thing works right now. So if you check out Julia's master and then if you build cxx.jl, you will actually get all this working without having to muck around much further. And that's essentially made it very easy for us to plug in libraries like ArrayFile. OpenCV is another one if you work with image processing or computer vision. All right, so here's a simple example. This is Hurricane Katrina off the coast of Florida. You might have all heard about it at one point. So we just downloaded a video of Hurricane Katrina and then we said let's run k-means on it, on every frame of the video and see if we can sort of separate out the clouds from the land, from the water, like just very basic segmentation of every pixel in the image. And that's how this thing came around. So this is weather satellite data for Hurricane Katrina. And so we have two versions. I have two videos out here. There's the CPU version and there's the GPU version. And you can, as I run it, you'll kind of begin to see what's happening. Oh, this is interesting. I have a different view here. Okay. So the CPU version is kind of started and it's got some ways to go. So you can kind of see that it's coloring, this is the coast of, this is the sort of the tail of Florida right here. This is, the Atlantic Ocean and this thing is kind of moving towards. This is not the original video, right? This is a video where on every frame k-means has been run. So this is real-time k-means and the video was captured. So this is exactly the speed at which the CPU does this algorithm.
That's a single CPU, yeah?
Sorry?
It's a single laptop CPU.
It's a single laptop CPU, so I'm not doing k-means on, I could have done parallel k-means on, but you'll see the point, right? I mean, it wouldn't have helped much. So, it's, I just started so much later, but it's just gonna go through and finish off. And I mean, this is why really people love GPUs, right? And this thing is kind of still going on. Oops. Right there. All right. So this is kind of now what was the code to do this was exactly the same. So it was just if you know k-means, it's not a very complex algorithm. It's probably 10 lines of code, and because of all the plumbing that I talked about, the GPU version, the CPU version are exactly the same, or maybe off by a couple of characters, AF array or just a regular array. So here's an example that I could actually fit on this slide. So I just took a different example to show. This is if you're in finance, this is the Black-Scholes PDE option pricing thing. And it's just a whole bunch of vectorized statements. I'm not a finance person, so I kind of know what options are, but I really don't know, how all this stuff works. But as a computer scientist, I'm like, oh yeah, I see these are all vector operations, and this code can work really, really fast. So this is the GPU version, that's the CPU version, and the code is exactly the same because it's vectorized, so you just pass in different inputs which are on the GPU versus the CPU. And here's what happens. So this is straight on vectorized Julia, and that's what it takes. And then this is devectorized Julia. So in Julia, because the compiler is really good, if you devectorize a code, you can actually run it much faster. And the reason, like you asked about GC, the reason it often runs faster is because of GC. It's allocating lesser memory, so there's lesser pressure on the garbage collector. So devectorized Julia is usually faster. and that's array fire, just like it's barely registering up there. We have another compiler project. It's called Intel's Parallel Accelerator.jl, and there's a blog post if you go to the Julia blog that talks about this. So this is the Julia vectorized version. These are not directly comparable because they're doing different iterations. So these two are separate graphs, but within the graph you can compare stuff. And turns out if you do the right kinds of compiler optimizations in sequential Julia itself, you can go using 36 threads, using multi-threaded Julia down to pretty much GPU time. And so whether it's multi-core hardware, whether it's a GPU, Julia has the tricks and enough information within the compiler to do all kinds of optimizations, and that's kind of what makes it really powerful.
Could we make the function templated on some T? And then
Yes.
Okay.
Yes. So instead of float 64, you could have put a T here, and then you'd have put a T here as well. So you right after the function.
End up having to write.
Exactly.
So suppose you wanted to self-block shells to 400 digits instead of just the usual. That's all you have to do. That's it.
Right. So you just put the T and everything's going to go through. Sometimes people do it this way because they want to enforce type safety. So they want the function to be called only if it's float 64s. And they may have a different algorithm for float 32s.
Couldn't you then specify what your T had to be within a set, or we had a union?
Yes. So you could give a union of types. Right. So there's a whole algebra on the types that works in the type system. It turns out that the type system within Julia is also Turing complete. So you can actually within the type system write any program, but you don't know if it's going to finish because it can't solve the hotting problem. So we have some nice blog posts coming up on this stuff soon. This is another library. I'm not going to spend time on it. This is a graph library on Julia. We plug on GPUs. We plugged it into Julia, and we used it to solve a made-up attack graph problem for intrusion detection. It's like a cybersecurity thing. So that works great. So this is just more Julia GPU kernel. So there's a bunch of stuff that Julia now has to work on GPUs, and it works well. And I'm gonna maybe have 5 more minutes. So I'm gonna quickly just now talk about what we've done with recommender systems. And this is the talk that I stole from. I just stole a few slides. But this was a great talk. I figured since you guys have had this talk, I don't need to actually talk much about it, and just kind of talk about what we did. So everyone knows what a recommender system is, and you have your consumers and the merchants, and you have the ratings, and you want to factorize the ratings matrix into this U times V, which is your user space, the consumer space, and the merchant space, and then find the optimal, it runs iteratively to solve this problem. Everyone knows this. So why Julia, right? And I think this might maybe convince you, a little bit more about why Julia is good for doing these kinds of things. I mean, by now you already know that Julia is, sort of natural for doing matrix operations, linear algebra. It's fast. It's got user-defined types, all that stuff. So this is essentially the whole algorithm, right? You have this outer loop of iterations where you're updating the users and then you're updating the items, right? So you have the two, and here's the update user function. There's an update items function that looks almost symmetrical to this. But you have your, it's pulling the data out of the ratings matrix, and then it's it's setting it up and it's solving it's solving every iteration, and you've got your backslash in there, which is essentially where all the time gets spent. But this is essentially it. That, the real code that actually does this has maybe a few more lines of code for setting up, reading the data, and orchestrating everything. But the meat of it is exactly just this. So PMAP is what distributes the. So if you're familiar with this problem, you can solve it. You can solve within every iteration. Each of these things can also be solved further in parallel. So there's like there's an outer iteration which cannot be parallelized because it's time dependent, but there's an inner one where you're computing columns of a matrix that can be parallelized. And that's what's happening here. So PMAP will distribute update user to as many number of CPUs as you have, and it's going to go ahead and solve it. And here, this is very new work, so I don't have nice charts unlike your talk. So we're still working on making the pictures. But on a lab, so these were the movie sets, the data sets we used that we had access to. We had a movie lens data set that had 20 million ratings. There's last.fm, there's 24 million. There's last.fm. We just concatenated it 4 times. And so that ended up with 96 million, or almost 100 million ratings. And then those are the number of users and items. And essentially, running on a laptop with 4 cores, 8 hyperthreads, essentially. We had 3 implementations. We had a shared memory implementation, so the data is getting loaded and into shared memory, and every process is using the shared memory. We had this version with blobs, which is essentially breaking up the problem into small chunks and working on them. And the reason I'll just talk about it later. And there's the multi-threaded version with the experimental multi-threading with Julia. And you can see that, as you'd expect, the multi-threading version is the fastest out there. Out here it's not because of GC. We have a global GC lock in the multi-threading, so the problems get bigger. It spends too much time waiting for the GC, so that will get fixed before we release the next version. But here's the version with blobs. So blobs is a framework which kind of splits up, your matrices into little pieces, and then it schedules them so that you're always working with little bits of data at a time. Many of you are probably using Spark, so you can already sort of start seeing the analogies with Spark when you see some of these things. So this data set, which is 100 million ratings, could not run with the shared memory and the threads version, because those 2 versions of the algorithm load the entire data set in memory and then it runs out of memory. But the blobs version actually loads the 100 million on a laptop and just runs through it, and it takes about like 15 seconds. It's like almost 10 minutes, right? Or 20 minutes or something like that. And the code essentially looks exactly like this. You couldn't tell the difference. I mean, all the 3 versions don't look very different from this version right here. And then, we sort of going forward, we have, so we're taking some of the ideas that we used to solve this ALS problem, and we have a poorly named project called Compute Framework, which we'll change the name of. So, we took some of the things that you see in Spark as well as Dask. Are there any users of Dask out here? I know that there's lots of Spark users probably. Spark? There's a few Spark users. Well, not many more than the people who raised their hands with Julia before, so that's very encouraging. Any of you use Dask out here? Okay. So these are 2 frameworks which work very well with out-of-core stuff. So people just love to solve as much as they can on their laptops or distribute it out of core. So we took all this, threw it together, and here's another last example before I finish up. So here's a logistic regression. It looks exactly like this. We have to use our Unicode variable names. We just love them so much. So this code, you'd have to really look hard to see that this is actually a parallel code that's running on this framework like blobs, which is working with pieces of data at a time and loading things into memory as it needs them. But you can see there's a gather out here and there's a gather out here. And that's essentially maybe a hint that maybe this is not a sequential code. It's kind of doing something and then gathering it later. But the rest of it is all sort of, all looks like sequential code. And this is the crux of the problem right here. So when you're solving a logistic regression, you have this big X transpose X that happens. And the X is usually millions of rows and a few columns if you're working with any real data, right? So one of the data sets that we ran this on was this ad click data set. So there are 45 million rows. So 45 million ads were shown, but for every ad you may only have a few dozens of pieces of information, like which IP address, or what's the classification of the person, is it male or female, or was the ad clicked or not clicked. So you may have like 20 or 30 such observations per click if you're serving ads. Imagine your Google. And so you have these large, tall, and skinny matrices which do not fit in memory. But it turns out that if you write your codes the right way, you can do X transpose X completely out of core and completely without blowing the memory of your machine. It just takes longer to run because it's loading parts from disk, and the whole thing goes through. So this is, in a few weeks we expect to have high quality things, high quality libraries that can do common statistical operations, common matrix operations on not just your laptop out of core, but even in distributed memory. Or at least we hope that we'll have these things. It looks pretty promising. With that, I will end my talk and take any questions. deep neural there's actually really amazing packages in Julia for deep neural networks. There are at least 2 that I know of that I like a lot. There's mocha.jl, which is a complete Julia implementation of deep neural networks, and it's nice to play with, and it's pretty sophisticated. It solves the whole ImageNet problem. There's also mxnet.jl, which is a more commonly and widely used code that has been that supports Julia as the first class thing. And Ben, did you write a deep neural nets example, or am I mixing up with someone else? Okay, all right. So yes, there are at least 2 that I know of, and there are lots of amateur implementations where people are teaching themselves DNNs and they write like 100 lines of Julia. But these 2 are production grade DNNs with full GPU support and everything.
Including visualizations of the weights.
I haven't used them, so I don't know that, but I believe they do have visualizations as well. Yeah. I must also point out that Ben has been one of the, you've done a talk out here before, but he's one of the largest contributors to Julia and has a very popular package called
Decision to jail.
Yes.
So random forest.
It's a random forest. Yeah, I forget the name because there's many random forest codes, so I can never remember which one is Ben's. But Ben's is the most widely used random forest code in Julia. It's very heavily used everywhere. And I just thought I'd mention that.
What's the best way to learn Julia? How do you get started?
It's a good question. Do you want to try, or?
So if you go right now to learn, go to julialearn.org and click on whatever the right tab is. Different people learn in different ways, right? And that's been well observed. Some people like the videos. David Sanders' tutorial might be. So yeah, if you can go to julialearn.org, you can see some of the ways of learning.
So there's some books. There's tutorials.
Are there any really good
videos
books right now?
No, I don't know. I think some of these are not.
I haven't looked at them yet.
They're okay. I mean, they're not bad actually. They're okay, but I think they're not what I would call the definitive books on Julia.
I've seen there's a Kaggle tutorial.
There's a Kaggle tutorial on Julia. There's a quant-econ tutorial on Julia, which is also very good.
Oh, yeah, people like that one, right?
A lot of people like this one right here. Oh, this is too small to see.
But just go to julialearn.org and you can see all of the choices and you can pick which one you like the best.
And there is a pretty comprehensive manual as well.
Is your course on OCW?
My course some of my notebooks are on GitHub. If you just have 18.237, I don't know how you remember that, but you probably got my name there.
Well, I guess you go Alan Edelman and then.
Yeah, I don't know if that will work. You have to find my course though.
Oh, it doesn't. Okay.
Just type 18337. There you go. And then go to the course GitHub page, which is just that. You see the course GitHub page, right? And there's some of the stuff is like if you go to lecture 1, for example. Go to lecture 1, you can see some things.
Just go inside there.
Yeah. So you can play with some of those things. But I don't know if my course is the best way to start. I'm not sure you get to start. I don't know. I like David Sanders' video tutorial.
I think David Sanders' video tutorials. It's a 4-hour workshop which is completely recorded, and it's.
I would go twice the speed, so you could do 2 hours.
I think he does a good job.
He does a pretty good job, yes. So I think he's here.
Is it over there? Over there, yeah.
Hands-on Julia by David.
I wonder why we have that last. We should do it first.
No, it's here actually. This is the one. It's right here actually. You can watch it right here.
Oh, it's like by 2014. Okay.
Yeah, and then he did it at Julia. But this was the definitive one. Like he really did a good job here.
And I don't know if this is a way to learn, but I love the fact that could you just take YouTube JuliaCon 2015 or something and see all the.
Yeah.
This isn't quite.
Well, you don't even have to do that actually, because if you just go to julialearn.org.
Well, let me rephrase
they remove the videos. Oh, there they are. So these are all the JuliaCon videos right here.
Yeah. They're all. But how do you see them in one place? Oh, there you go. Okay.
Let me rephrase my question, because you're right. Not everybody learns the same way. It starts with not everybody has the same background. So for a data scientist, machine learner with a background in Python.
Right.
That's the best way.
We need to write those things.
Okay.
I still think watching David Sanders at speed It's not a bad way to start. And then pick something that interests you, maybe out of the Julia con, and then see if you're ready for it. You know, you might. Some people might be fast.
I've seen people also learn Julia by, so juliabox.org is one of the things you could do where you log into Julia. It's running on the cloud, and then you can just sign in with the Google account. Let's just see if I do this.
Yeah, so you don't have to install Julia to start working with.
And you get the notebooks out here, but if you log in the first time, you get like a basic tutorial in there, and then people just follow those. It's a very simple tutorial, but it gets you going. And that's another thing I've seen people do.
Can we get 80 cores on JuliaBox?
We're trying to set it up so that you can buy per hour.
Oh.
Yeah. So we're already running out of money giving the free half a core.
Yeah, Amazon sort of gave us an initial amount of money for, you know, we're really coming to the end of that.
Yeah. So there's this thing called tutorial in there, and this is Steve Johnson's tutorial, and it's just got a few basic things. And it's pretty good actually. This is also from EuroSci-Fi. This is EuroSci-Fi, not sci-fi. Yeah. It turns out some of our best tutorials and work is done in the Python conferences.
I noticed Googling for Julia videos, it keeps coming up at PyCon.
Yes, yes. So, I mean, that's the right place to watch it if you're a Python user, right? Because we keep all that material was
keep
made.
getting invited, right? People in the Julia community keep getting invited.
Yeah, we have a really good sort of equation with the Python community. There's, we have Python speakers come to JuliaCon, Julia speakers go to Python conferences, and like, you can call Python from Julia. Actually, you can call Julia from Python, like all the way. All right, I think people might want to leave, so we'll hang around if some of you guys want to talk to us, but we'll, thank you all for coming.